law. Previously, we looked at thermochemical equations and how to relate enthalpy change to stoichiometric ratios. So we're taking a look at how else we can determine the enthalpy change value for a reaction given different pieces of information. So Hess's law states that the heat of a reaction is determined algebraically by adding the values of enthalpy change for different but related reactions. When we add these reference reactions, it will give us our desired or our target reaction. When determining enthalpy change, it is important to either reverse and or adjust the molar ratios by multiplying that enthalpy change by a specific factor. So here are the following rules that must be included when we are using Hess's law. The first one states that if a reaction must be reversed, the sign of the enthalpy change for that reaction is also changed. So let's say we had a reaction and the enthalpy change was 38 joules. If I reversed or flipped my reaction, so I manipulated it so that it was once A plus B equals C plus D, and now I'm saying I want my reaction to be flipped, then your enthalpy change should also be flipped by adding a negative sign. Or if it was a negative value, the enthalpy change is now a positive. The second rule states that when adjusting molar ratios by multiplying, all coefficients in that equation must be multiplied by the same factor, as must the enthalpy change value for that reaction. So whatever is done to that reference equation must be done to its enthalpy change value as well. So referring back to this, let's say now I wanted to multiply my entire reaction by 2, meaning all of my reactants and products will have a coefficient of 2. That also means that the enthalpy change value will be multiplied by 2 as well. Okay? So that's 76 joules. Okay, so let's take a look at a couple of examples. The first one says carbon solid reacts with water vapor to form carbon monoxide gas and hydrogen gas in the following reaction. So this here is my desired reaction. It says use the following reference equations to calculate the enthalpy change value or the delta H value for this reaction. I'm given 3 different reactions as well as their delta H's. So this is the delta H specifically of carbon in reaction 1, delta H for carbon monoxide, and delta H for my H2. So if we take a look at the first one, we will compare the position of carbon to my desired reaction. So since carbon is on the reactant side in my desired, I'm going to keep it as is. Okay, so you can say we're multiplying everything by 1. We keep this reaction as we see it. The next one is for carbon monoxide. You can see that carbon monoxide is on the reactant side for reference equation 2, but I want it to be on the product side on my desired reaction. So I'm going to multiply this reaction along with its delta H by -1. And then lastly, for my H2, also multiply by -1 because in this equation 3, it's on my reactant side, but I want it to be on my product side. So you can see if I rewrite all of my equations, so the first one stays the same. The second one, I have flipped it. And the third one, I have also flipped. Okay. Now we take a look at all of my equations. Whenever you see something on both sides of the reaction and it's the same substance, we can cancel it out. So for example, carbon dioxide is on my product side as well as gaseous carbon dioxide on the left in my reactant side. What else? So we have half and half oxygen as well as one whole oxygen molecule on the reactant side. So these will add up to form one. And because they're both, oxygen is on our reactant and product, it cancels out. So now what we're left with, the substances that we cannot cancel out, will give me the following equation. So solid carbon, gaseous water, or H2O, carbon monoxide, and hydrogen gas. And this is what I was aiming for. This is my desired reaction. So in order to figure out your delta H for this desired reaction, we can add up the enthalpy changes for each of the reference equations. So the first one is negative 393 kilojoules per mole plus, remember I've reversed my equation, so negative 283 is now positive because negative 283 times negative 1 is 283. And then same thing for my third reference equation, negative and a negative, 242 kilojoules per mole. So adding this all up will give me 132 kilojoules per mole. Okay, so negative 393 plus 283 plus 242 is 132 kilojoules per mole, positive 132 kilojoules per mole. So this reaction here is an endothermic reaction because my delta H is a positive value. Okay, so I want you to try the following examples on your own and have them prepared for class tomorrow, and we will take it up